Hi everyone, this is Maths for Uni. This is question 2 from the worksheet corresponding to lecture 4. If you enjoy this content, then please consider liking and subscribing, and also checking out our Udemy course, of which the link is in the description. The question says, show that f from the integers z to the natural numbers n, with f of m being defined as 2m for m greater than 0 and two lots of minus m plus 1 for m less than or equal to 0 is a bijection. So recall that if we want to show that this function is a bijection, then we need to show that it is injective and surjective. So if we start with injectivity and trying to demonstrate this, then for injectivity, we want to show that if f of m equals f of n, then m equals n. So in order to show this, we look at the individual cases that we have above from our definition of f. So let's say we take, as we have, f of m being equal to f of n. Then we have 4 separate cases depending on whether m and n are greater or less than or equal to 0. So in the first case, let's say we have m greater than 0 and n also greater than 0. Well then, f of m equals f of n, this result here, tells us from the definition of our function that 2m for f of m and 2n for f of n are equal. And this, quite simply, by dividing by 2, gives us m is equal to n, as we require from our injectivity condition. But we still have 3 more cases to check, because m and n are integers more generally. So the next case we could take might be m greater than 0, but instead n being less than or equal to 0. The left-hand side of our condition is still 2m, because m has not changed from being greater than 0. However, n is now less than or equal to 0, and so we're now on this part here of our function definition. And so this gives us 2 lots of minus n plus 1 for our f of n. However, this is in fact a contradiction. We cannot have this situation because the number on the left-hand side is even, because m is an integer, and the number on the right-hand side is odd, because n is an integer. So we have a contradiction, i.e. if we assume that f of m equals f of n with m being greater than 0 and n being less than or equal to 0, then we get a contradiction, and so this case in fact cannot occur. Next we have another very similar case. We have m being less than or equal to 0 and n being greater than 0. However, this is essentially the above case with m and n being swapped. And so if you work through all the algebra, you will indeed again get a contradiction. Next, the final case is both m and n being less than or equal to 0. Now we have f of m being 2 lots of minus m plus 1, and similarly for f of n we have the same thing, but n replacing m. And so again, if we rearrange this, essentially just like the first case, even though that was slightly simpler, i.e. we minus 1 from both sides, divide by 2, and ignore the minus signs, i.e. times by minus 1, this still results in m being equal to n. And so in the cases that don't give us contradictions, we have f of m being equal to f of n implies that m equals n, and therefore we have injectivity. Now, for bijectivity overall, we still need to show surjectivity. Recall that for surjectivity, we want to show that for every value in the range, which is n, the natural numbers in this case, looking at our definition up here, that there exists a corresponding number in the domain, which is the integers z, such that applying f to that number in the integers gives us the number in the natural numbers. So in symbols, we can fix a natural number n, and then we want to show that there exists an m in the integers such that f of m is equal to n. This is what we need to show. So let's say again we fix a particular natural number n, then there is two cases, or rather there are two cases on how to proceed dependent on whether n is odd or even. Firstly, let's take the first case in which n is even. In this case, if we want to choose an m such that f of m equals n up here, then we can choose m to be n over 2. N is even, and so n over 2 will certainly be a natural number, and more generally, an integer. Then f of m will be 2 lots of n over 2 because m is positive, because n is a natural number, and this gives us n as required by our condition. So we checked the required condition for the case that n is even, but we need to do the same for the case that n is odd. If n is odd, then it turns out that we can choose m to be minus n minus 1 over 2, and we choose this because then f of m is equal to 2 lots of minus n minus 1 over 2, the value of m, and then plus 1, because m will be less than or equal to 0. The two minus signs cancel out, and this gives us 2 lots of n minus 1 over 2 plus 1. The 2's cancel out, giving us n minus 1 plus 1, and then the minus 1 and plus 1 cancel out, giving us n. And this is why we chose m as above. In both cases, we have shown that there exists an m in the integers such that f of m is equal to n, and therefore we have surjectivity. If we combine the fact that we've shown injectivity with the fact that we've shown surjectivity, then overall we have shown bijectivity. So indeed, the function f is a bijection. Now it's worth being aware that we refer to sets that are bijective with the natural numbers as countable. So what we've done here for this particular f is to show that z, the integers, is countable. For a demonstration of why the natural numbers r is uncountable, in fact, see Cantor's diagonal argument. Cantor's diagonal argument is a classic example within the field of countability, and it's worth seeing at least once. If you found this content useful, then please consider liking and subscribing, and also checking out our Udemy course, of which the link is in the description. Thanks for watching, and goodbye for now.